It's great to be here. I guess I know that this is probably an audience with more optimization statistics background. But recently I think I'm moving to some of these empirical areas. So this is something that I spend most of my time on. So I thought it's probably uh, still better to talk about this than some of my optimization work. And I'm going to try to make this entertaining to some degree. And I think maybe just to start with, some of the motivations. I think one of the motivation was that, one of my students was working on theory for deep reinforcement learning for 3 years, and we get some papers, and we were, pretty happy with the papers by themselves, but we couldn't push more to the, like we couldn't understand more. Like it sounds like we are hitting a wall, as deep learning theory in some sense. So then we say why not we flip it so that we don't use math to understand deep reinforcement learning, but we try to use deep reinforcement learning to do something more about math, and that's one of the reasons why we start this. And another reason I think is I think let me see how to wait. Does this work? Sorry. Okay. One of the reason is Another reason is that I had a bet with some of my friends, I guess Jacob and Stanford and Sean Kakady. And we were in one of this workshop in Germany, like around I think that's 2023, October or September. I think the email thread was like October. So we had a bet, about when AI can solve IMO questions. At that point, I said, how do I make this go away? Let's see. Should I? Okay, and yeah. So basically that's right before, I think actually the last email in this email thread was right before the release of ChatGPT. So we were debating on whether AI can solve, when AI can solve IMO questions or all IMO questions. Um and and I was on the side of like no, and other people, almost every other people say by 2030 AI can solve all IMO questions. And now in 2026, I think I already lost the bet for a year or something. So I think the story was that I realized that I was gonna lose probably by 2024, maybe maybe early 2024. And that was one of the reasons why I started a startup, but that's a separate story. And then on the other hand, I thought, okay, maybe there is some ways for me to hash this bet so that at least I get something out of it from this AI wave. And I thought, oh, maybe let's try to also try to prove more theorems, try to contribute to this area. Of course, eventually, proving IMO questions doesn't require my research, but I was trying to do something along this line. So that's another reason why I try to work on this AI for math. And now, I think after I gave this talk several times, I think I'm getting into more bets. I think one of the bets I had is with my colleague at Stanford, one of my colleagues at Stanford. And this time it was about whether we can solve Riemann by 2030. I'm still on the side of like, no, it's not gonna be solved by 2030, but I think, at least someone is willing to bet with me on this with equal odds for Raymond by 2030. We'll see. I spent actually like after I made the bet, I spent like 5 hours working with ChatGPT to understand what's the landscape of Riemann Riemann hypothesis right now. Unfortunately, I don't think I can judge how fast we can prove it. Anyway, so okay.
What's IMO?
IMO is International Mathematics Olympiad.
Oh.
Yeah, this is the high school Olympic questions. So yeah, and now you can solve all of them like easily. Like you just use ChatGPT, you just copy and paste the theorems and that like you don't even need scaffolding, nothing. Just it's always solved.
Before ChatGPT.
In 2023, 2023.
2022, right?
Oh yeah, it's 2022, not 2020.
So
Wait,
it was just before ChatGPT.
it's right before ChatGPT.
What did they expect? They said before 2000.
I think they were probably they would be willing to bet with me for maybe 2028 as well. Yeah, but maybe not, but not 2025. Yeah, I think I got all the year wrong. Like, yes, we bet it in 2022, and I think I started to work on this in 2023. You know, around the time that I started startup as well. So yeah, so I think, but I think they were thinking about 5 years, maybe 5, 7, 6 years. Yeah, yeah. Anyway, yeah. So I think actually I asked like probably 10 people, maybe at least 10 people, 15 people. I think there's a correlation with the mathematical, like the only people who barely agreed with me was somebody who also did IMO in their past. And I think there's some kind of biases introduced because you feel that what you have done was kind of difficult. Yeah, I know. I'm not sure whether I should say it on the records, but I think similar things is happening right now as well. Like when I talk to mathematicians, I think you can, um, uh, at least you can see the differences between mathematicians and computer scientists in the predictions for these kind of things. But another thing is that I think the things are changing a little bit as well. Maybe just as a side note, because I think OpenAI is not making more investment in this anymore, which is sad in my opinion, because it's probably, at least it's probably a bad thing for the AI for math community, because we lose the investment and the money invested in this, partly because OpenAI is kind of having some troubles with Anthropic about coding and enterprise business. So it sounds like OpenAI is trying to narrow its effort to compete directly with Anthropic.
When
Sorry, why? Which part?
this OpenAI is not putting money into this.
Oh, I think that's almost like an obvious. Of course, I don't have proofs for it, but there are enough kind of like a either news from the information, or I'm not sure whether you know the information, the Silicon Valley rumors, kind of like a newsletter, and from all the you talk to folks who like they are all kind of like leaks. OpenAI seems to it's pretty obvious that OpenAI is changing directions and narrowing its focus, right? Like just that's almost obvious. Like there's so many kind of internal memos and all hands, Sam Altman's kind of speech, all of this. And I think AI for math is one of the things that might be cut, or at least partially cut. I don't know, I cannot be 100% sure, but this is what I hear, almost like consensus. But another thing is that even the cut effort, it doesn't necessarily mean that the math capability doesn't improve. Sometimes you just like some of these things doesn't necessarily require more efforts. It's kind of like you just use your existing recipe and tune for longer and longer and longer. Maybe you just get better and better. So we'll see. And maybe another thing is that whether math is whether OpenAI reduce this effort on math is probably something that you can never know exactly, but it sounds like OpenAI is trying to compete with Anthropic on enterprise. That's very obvious, almost. Yeah. Anyway, okay. So let's talk about some more technical stuff. So I guess I'm going to talk about reasoning capability. I guess I used to say that the reasoning capability appears to be the only barrier between us and AGI. And then I gave this talk several times, and I found that it's still a little bit controversial. I think maybe let's not debate on that and just say reasoning means coding plus math, and probably mostly math for this moment, because coding seems to be solved by Anthropic Opus 4.7 and GPT 5.5. I think it sounds like the remaining coding questions are actually about reasonings and some of this mathematical part. Anyway, so let's say suppose your goal is to solve more and more math open questions, and one of the common question, maybe there's less of a concern like this anymore in 2026, but at least last year when I gave the talk, the most common question is, do you really believe that you can solve Riemann hypothesis of P versus NP by large language models? And the common concern is that maybe large language models still don't understand and just pattern match. And here's my response to that. First of all, I think all of the existing approach before about automated theorem proving clearly doesn't understand. If you compare large language models understanding versus those understanding, those previous approach, I think it's not controversial to say at all that a large language model understand much better, right? Because all the lean automatic search algorithm, they're just search machines, right? You just search and you don't understand, you just try to find out something that is correct by lean, right? And the second point is that, in some sense, interestingly, large language models are very, very similar to humans, at least more similar to humans than any of the other methods we have considered. For example, humans have vague intuitions. Sometimes you extract the vague intuitions from few short examples. Humans do a lot of pattern matching as well. I think, at least for me, when I try to prove something, especially if I get into some new areas, I pattern match first, and then try to understand more, so on and so forth, right? And you want to prove one theorem, you find all the similar theorems, even just on the surface level, and then you figure out which part is more useful, which part is not. Hallucination, first of all, large language models don't hallucinate anymore that much. And when it hallucinates, sometimes it's a good thing for mathematicians. I think like you need to have some imagination to even guess a wrong proof to start with. I think one of the talks I heard recently is that a physicist said that a wrong proof is better than no proof. So you need some imaginations to even start with a wrong proof. And self-reflection is what humans do a lot, and this is achieved by long chain of thoughts. And also, interestingly, the incapability of long precise mechanical deduction, I think that's actually still a limitation for large language models to some degree. I don't know for sure 100%, but at least the first version of this talk was like 6 months ago, and at that time when I read this line, I go try ChatGPT, the latest version of ChatGPT, and I try to let it add 15 numbers without long COT, without tool calling. I still have some small mistakes. Without any COT, nothing, right? Just the one short addition. Of course, it's not. I'm not saying like I'm using ChatGPT for my personal finance. I trust it 100%. But I'm just saying like it's not that easy for the large language model to do the calculation. I think tool calling seems to be the right way to go. And the same thing for humans. Humans don't do that kind of like precise deductions very well. Okay, so now why formal theorem proving? The whole talk is about formal theorem proving. I think this is one of a common confusion, at least confusion of my opinion in some sense. Like, I wrote papers in formal theorem proving, and I had a few papers on that. But I never really necessarily believe that formal theorem proving is the way to get to AGI, to get to prove Riemann. I only use it for convenience, and the convenience comes from that you have this verifier that you can verify objectively. You don't have to hire PhDs, with mathematical PhDs to label your proofs, right? So OpenAI have that resources to get either in-house or contractors to label their proofs, but we don't have the resources. So that's why we have to have some objective, reliable evaluation. So it's both evaluation and also verifier in your RL algorithm, right? So you may use a large language model verifier, but you need some objective evaluation for academic research that is some kind of like scalable. And also when you have the formal theorem proving, you kind of believe that maybe you don't have to care about the natural language that much, so you can reuse the parameters in the pre-trained checkpoints for natural language to more mathematical capability, hopefully. Again, one of the caveats, I have question mark theory because worlds are changing so fast. I think it changes the ways that we make slides as well. Like I used to make slides like once every kind of like maybe 6 months, and give the same talks, for 6 months. But now, like, unless you put more actual works, I have to fact check my statements. So this I think was a true statement, but now whether it's really a true statement, I think is questionable. If you use open source customized formal provers, of course, it's still not as good as ChatGPT. But if you just use ChatGPT to generate lean proofs, I think they're actually pretty good. Of course, you cannot really do like hard theorems which are not even having libraries like there are a lot of theorems that you cannot even formalize because you don't even have the libraries for it. But for those other ones, I think maybe formal provers are already catching up. But anyway, for me, it's only for convenience. I don't know which one will win. Maybe the natural language capability will be improving much faster than the lean capability, or maybe vice versa. We'll see. Anyway, so these are the lean proofs. They are very similar to natural language proofs. The only thing that is kind of like interesting is that there are this kind of like tactic, like lean arithmetic tactics, which basically simplifies a lot of calculations. So basically, this will figure out how to linearly combine all of these equations into a conclusion. It's like solving an LP and SDP under the hood. And if you have a natural, if you have human writers, I think most likely you're going to give the certificate for the linear combinations of the linear equations and say, oh, this is my certificate, so that's why I got this conclusion. But the certificate is searched by the LP and the SDP under the hood, and oftentimes the certificate is not even given. It just says linear arithmetics, and you don't see the certificate. So this is a little bit small trouble. Sometimes you can even use sum of squares, right? So it's actually, when we train these models, we try to disable sum of squares, because when you allow sum of squares, so many things are so easy. You just use sum of squares, and all the linear algebraic equations get solved. Sorry, all the algebraic inequalities got proved. And you don't learn much from it. So you have to disable some of these powerful tools to at least learn a little more about arithmetic manipulations. But beyond that, I think they are almost the same. It's just a formalization so that you can use the machines to check the correctness. Okay, so, and this is how people are training these models, typically. So this is what O1 is doing, what DeepSeek R1 is doing, and what DeepSeek Prover V1.5, V2 are doing. So the DeepSeek has this specialized math prover, 1.5 and 2. I think maybe there's a 2.5 now as well. So it's a very simple RL algorithm. So basically, as in any other algorithms, you collect some statements, and you are given the statements actually, and you generate your own proofs. That's kind of like you are generating your actions. And then you have a reward function, which is given by a verifier, either is a large language model verifier or lean verifier. And then you select all of the proofs that are correct. And then you just discard all the other proofs and only reinforce all the correct proofs. So by reinforce, it just means that you do like SFT, you just fine-tune the models on the correct proofs. And you do this loop. That's basically reinforcement learning. I think the issue is that, maybe the question is that, do you really believe that this can be run forever until we solve Riemann hypothesis, right? If that's the case, that would be great. You just keep training it until you have the Riemann as one of the statement, and you keep trying error until one day you can solve Riemann. My opinion is that it's probably very hard, and the evidence seems to be that most of the scaling laws for these kind of algorithms are pretty bad. If you look at the original OpenEye blog post, that's like probably 1.5 years ago, maybe even 2 years ago, August 2024, I think. So they, visualize this scaling curve. The x-axis is the log scale, and the y-axis is the accuracy. So basically, double your compute, you only get additive constants in accuracy. And then later, like October last year, Maita has this paper which does a little more kind of like careful scaling analysis across many different kind of algorithms and the initial checkpoints, data sets, so on and so forth. And they found that it's always this kind of like, actually it's even worse than linear in log scale. It's actually a sigmoid in the log scale. So there's a linear regime in the log scale, and then after that, it's actually slower than linear in log scale. And there's a ceiling A, which is something that you cannot break. So basically, in a priori, the best performance is 100%, but at some point, you reach this probably 80%, and then after that, the rest of the 20% you can never solve at all, and you never have any reward for them, and you just get stuck with. So this is actually very typical for most of the RL algorithms and data sets I've seen. Like there's always some ceiling. You don't know whether the ceiling can be raised because you don't know whether there's any other new algorithms. But for the fixed algorithm, you always see that it plateaus at some point.
And the problem solved, what is being measured?
Yes.
That's not really the right way to measure hardness, right? Like that's kind of a mistake way of.
What's the better way?
You wanna, that's a good question. But this doesn't tell you if you can solve Riemann hypothesis by running RL, right?
Why? Because this is actually a much simpler data set. Let's say suppose you have all the
Riemann hypothesis is one problem.
yeah, I
It's a
know.
very specific hard problem. So this
Yeah,
is
but if you can only solve 80% of the pull-down questions, you cannot even solve the rest of 20% of the pull-down questions. I don't think you believe that you can solve Riemann, right? And you are not making any progress.
That's true. I mean, it goes one direction. So if you can't solve a lot of, like, if this is bad, then I agree with it. It's likely you're not gonna make progress.
Okay, so but then what about you just put Riemann in it?
No, but that's not measurable. That's my question. Like, how could you measure progress towards Riemann hypothesis? Like, you have a very specific.
The answer is no progress, right? You just put Riemann here and you get a 0 forever. Right there.
That doesn't say anything. Like, I'm just wondering if there's a better benchmark for
I maybe tell me what's the problem with this benchmark? Maybe
the problem is like if the percentage of solved problems does not tell you the likelihood that you will solve a hard problem, like a specific hard problem. Because it's a 0-1 thing, right? It's not like you're not talking about generalization, right? The question
Yeah.
of solving, like your ability, you're trying to learn model's ability to try to solve a specific hard problem. There's no like almost correct. Are you correct? Or are you like, did you solve it or did you not solve it?
yeah, but I don't know, yes, you are right, in theory, yes, there could be a cases where like you solve 85% of pull-down questions and fail on the 15% of pull-down questions and you still solve Riemann or still have higher chance to solve Riemann, but I think this is a reasonable enough approximation. And also I don't know what does it really mean by the likelihood of solving Riemann, right? If it's not solved,
Exactly, that's the problem, right? Like that's about these, like my issue with these benchmarks, they don't really get to the heart of the matter, right? Like they're kind of, there's a problem with like if you care about solving hard problems, not solving problems on average, I guess. Yeah, there's no good benchmark for measuring such things.
I don't agree with this because I think it depends on whether maybe we don't have we can take this offline, but maybe my comment is that your argument applies to every benchmark.
For math, yeah, I agree.
Not for math, for everything.
Yeah, but typically generalization, like we care about generalization. But for math, we don't care about generalization.
You can have actually I'm not sure whether this one is exactly generalization. I think you actually can measure generalization. I think actually it's possible that some of these plots are for generalized settings. So I think actually the Amy one is generalization. You don't train on Amy, but you test on Amy.
I know, but I'm saying like if the question we can still take this offline, but I'm saying if the question is will you solve Riemann hypothesis, the question of generalization is not telling you will you solve Riemann hypothesis. The question of generalization that we usually think about supervised learning is meaningful for supervised learning, but not for that. Because you're doing something completely out of distribution. You're testing something completely out of distribution. And so I feel like benchmarks that people often think about are not indicative, like I'm not talking for math, they're not indicative of like, will we be able to solve like Riemann hypothesis? Because there's a very different, because they're really explicitly doing something out of
okay, anyway, let's take it offline. Yeah. So I guess my argument is still like I don't see a better way to do it anyways. And I don't see there was a better way to do it for other cases to some degree. But anyway, so and in my opinion, it's kind of pretty clear that this suggests that it's very unlikely to solve Riemann this way because you cannot even solve some of the existing data sets. If you cannot solve 15% of put-them questions, or you cannot solve 15% of like any data sets, right, forever, and you get stuck there forever, it seems to suggest that it's very hard to believe that this algorithm can keep going forever and just work, right? So and I think the reason, in my opinion, is that these are not really the reason. This is kind of still on the surface level. So the observation or the hypothetical kind of like the shadow version of the reason is that the more advanced the theorems are, the fewer they are, right? So you don't have that many. You probably have like millions of like high school questions. You have like probably millions of like archive papers, but you don't have like millions of like open questions like Riemann hypothesis. So you don't have like enough training signals once you go more and more advanced. Another thing is that for all these advanced questions, your pass rate is very low. So the chance you can find any successful proofs becomes lower and lower. And sometimes it's just that you have to try a million times and get one proof. Actually, that's actual success. If you can really try 1 million times to get one, at least you have one you can reinforce. But if you have nothing, then you cannot reinforce at all. So it's a sparse reward problem. So it's both lack of data and sparse reward. And as you go, kind of like a more and more advanced. So, and that's why I think why we got stuck here in the previous plot, because most likely those problems that are now solved here are just too advanced so that you have zero reward for them. And the questions here somehow cannot, are not kind of like you don't have enough questions in this regime so that you can extrapolate to the other more advanced questions. So like if you really have a lot of questions, suppose these are the high school questions, right? Then likely you wouldn't actually have such a ceiling, because training a lot of high school questions probably can let you extrapolate to a little harder high school questions, right? But I think as you're going more kind of like advanced, then because you don't have enough kind of like questions that have successful reward, the extrapolation is also not good enough in some sense. Anyway, this is just a speculation. And then I was wondering, why humans can actually improve, right? So if you think about it, right, so like a large language model in 2023 is at least as good as humans in 1300 problem. I used to have 1500 there, and then I used to have 1600 for the first number, and then someone in the audience told me that, 1600, you already have Newton, and it's kind of debatable whether large language model 2023 is better than Newton. So that's why I had 1300. I think the point is still true. And this, I think, is also very objective, 2025, 1500. And this one, I think, I don't know what number year I should put here. But anyway, so the point is that somehow humans improve from 1300 to 1500 to 2025 all by self-improving, right? Like it's not like humans get all the data that generated during this time, right? Among this time are generated by humans themselves. So humans as a race, they generate a lot of data themselves and then train on them in some way. There is no additional training data at all. So basically, if you are into 1300, if you think about it, all the data, all the new data are synthetic. There's no any more data, right? So that seems to suggest that large language model should be able to do that as well, right? Because because I think in some sense we do believe, at least I believe these days, that neural networks can simulate human brains very well, and even better in many cases, because there's more kind of like neurons, there's more compute in the neural networks than human brain. So why we are not seeing this effect that large language models can improve over time, if indefinitely? I think the reason is probably just that humans are not just trial and error in silos, so it's not the same algorithm. Right? Humans conjecture, humans review other people's paper, humans learn from other people, so on and so forth. So in some sense, the agenda here is that maybe we should simulate humans even more, and see how humans develop math collectively even more, and change our algorithms from this relatively simplistic RL algorithm. And this is a step towards that. So basically, we try to design, make the AI also conjecture, right? This is taking inspiration from mathematicians that, in math, you do want to practice on variants of existing theorems. You want to propose new and prove new conjectures. And apparently that's useful for mathematical development. And we try to let AI to simulate that. The algorithm is very simple. So basically, you have two rows. Actually, it's the same large language model with the same weights, and one row is the conjecturer. That conjecturer conjectures some conjecture y, and these conjectures are synthetic curriculum data for the prover. And then the prover will try to prove the conjectures by our algorithm as usual. And then after it tries, it can give some rewards back to the conjecturer to tell the conjecturer whether the the conjectures are good or not, and so that the conjectures can improve themselves as well. And also they share the weights, so sometimes when the prover becomes more intelligent, the conjectures can also be more intelligent. So here is the loop. So I guess the shade errors are the new part. So you conjecture, technically we also give the conjecturer a seed statement and a proof, and let it generate related conjecture. This kind of like makes the diversity a little bit better and also make it a little bit more targeted. And then you try to prove all the existing statements and all the conjectures generated. And you verify. And after you verify, you can reinforce the prover. When you reinforce the prover, you collect all the successful proofs, whether it's for the conjectures or for the statements. As long as they are correct, you reinforce them. And then you also reinforce the conjecturer by using a conjecture data set. And this is pretty much the only design choice here. So how do you reinforce the conjecturer? What is a good conjecture? What is a bad conjecture? And so we have 4 adjectives here, but actually they're not very hard. They're very simple: approachable, challenging, elegant, and diverse. So approachable and challenging means that the pass rate for the prover should be between 0 and 25%. Of course, 25% is just an arbitrary number we put in empirically. So basically have to be strictly bigger than 0, because that's how you know the conjectures themselves are correct. If it's 0, then you don't even know whether maybe it's just a fake statement that is wrong. And the upper bound is there because you don't want the conjectures to be too easy, because then it's not providing enough training signals for the prover. So that's relatively standard. Actually, no, everyone is doing this. And then we also found out that you need an ad hoc elegancy filter to try to make sure the conjectures are elegant. I'm going to talk more about this in the later part of the talk. And we also add some ad hoc tricks to deal with diversity. I'm going to talk about that a little bit as well. But for this paper, which is published 2025 January, these are very, very ad hoc. We just add some kind of like code to try to filter these kind of things. And then the prover data set is the same. So basically, that's the main idea. And just give you some examples on what we can prove. Last year, like January, with 7B problems. These are the natural language statements. They are generally very simple, not even high school level in some sense. Like this is probably just a barely kind of entry level high school computation problems. But now it's much stronger. And these are some examples for the generic conjectures. At that point, we couldn't even find much nicer ones than these ones, which is kind of trivial. Like you see, like you have a C statement, which is like 1 plus x squared is less than 1 plus x parenthesis squared. And then the conjectures make it a little bit more complicated to make it like x to the power n. So in the second examples where you just try to kind of like simplify the statement to make it more general. But in that case, like 1.5 years ago, this is the level we are dealing with. The conjectures are barely just paraphrasing some of the statements to make it a little more general or more complex. But the results looks pretty good. So comparing with the baselines, which is the standard reinforcement algorithm, is called expert iteration as well, or reinforce. We can see the scaling is much better. We have this data set with 89 high school level formal statements. Actually, 50% of them are actually incorrect. But you only count how many you can prove. So and you can see that the scaling of our algorithms SDP is much better than just the reinforcement learning, which is expert iteration. And you can start this at any checkpoints, and you are still doing better than the reinforcement learning. So basically, at every stage, this is helpful. And at that point, we actually had the state-of-art results, but this is like nothing in 2026. Like these numbers are, right now I think you can prove like 300 problems, probably. With a bigger model. With like 7B, you probably can prove like 50. With 32B models, you can prove probably 300 in the Putnam batch. And there are some ablations, which are just trying to reconfirm that some of the hypotheses, for example, the conjectures are much more approachable than the statements in the data set. So the statements in the data set has a much kind of like a longer tail in terms of the pass rate. So there are a lot of like statements that have very low pass rate. But when you look at the conjectures, then the pass rate is kind of more uniform. Some of them are easy, some of them are hard. And this gives you more training reward, basically more successful proofs. And then let me talk about some of the things we didn't dig into. One of them is elegancy, one of them is diversity. So so this was one of the problems we found during our research process. So if you don't do anything about the elegancy, then the conjecturers just go rogue by generating this kind of like seemingly very complex problems. They are both approachable and relatively hard. So these are correct statements, and there are some kind of non-zero chance to prove them, but they're also not that easy for the provers because it's very complex, long context, many kind of variables and equations. Eventually, most of these statements, if you try to find out the right combination of the hypothesis, you can prove it very easily. Or sometimes the combination of the hypothesis is just empty, like a false statement, so that every conclusion is true. And there are many examples like this. And this is another example where we lose the diversity. This is also an interesting case. So basically, at some point, we found that conjectures actually collapse to inequality mode, so that everything becomes inequality. So for example, if you give a statement about number theory, like this, P is a prime, then P divide A squared means P can divide A. And then it's supposed to generate another number theory statement, but it generates something that looks like a number theory statement, but actually it's really just about inequalities because the fact that it's a prime is not really heavily used here. So basically you get all of this kind of like a fundamentally algebraic questions, but they are disguised in the number theory kind of like language. So that's why we had some ad hoc filters for this kind of diversity. We have some training objectives to encourage diversity, which is kind of ad hoc. So let me not bore you with those kind of like details. And then later, we try to find out some ways to fix the elegance issue. So in the original paper, in the first paper, we used this elegancy score, which is the length of the shortest proof divided by the length of the theorem statement. So basically, you want the length of the shortest proof to be long, and you want the length of the theorem statement to be short, so that you say this is an elegant statement. I don't think it's really the definition of elegancy. It's just one of the approximations that we use, which helps a little bit. And in my opinion, a more principled approach is that you just use LLM to decide. Of course, you probably have to train the LLM to know some of the taste, but you just do a kind of like a fuzzy neural network based decision on the elegancy or taste. So that's why we had this another paper where we basically just changed this part. Of course, it also involves other infrastructure engineering work to make it scalable, and we work on bigger data sets, bigger models, so on and so forth. But generally speaking, conceptually speaking, the only difference is that we have a new elegancy score, which is decided by a large language model. You just prompt it by saying that your conclusion needs to be concise. You need to have some kind of like no redundancies in the premises, so on and so forth. Still, I'm not really happy with these kind of prompts. It's still a little too specific about the length or the complexity of the statement. It's kind of like you are fixing one problem, but not the general problem of the elegancy. But I think it's kind of like some partial progress towards this. And you can see that it does help. I'm not sure whether this kind of like the text here is a bit small, but generally speaking, what happens is that if you don't add this elegancy filter or this elegancy score to encourage the generator to generate elegant statements, then at some point the statement length it just becomes too long. But if you do it, then everything seems to be kind of relatively concise and elegant, to some degree. And eventually it will result in better scaling performance. So comparing this, you can see that actually, so I think we made some scaling loss. I think this one, if you extrapolate, it would actually a ceiling of like 67.1, which is quite above like a much larger model's kind of capability. So it helps a little bit. But still, the problem is that you can see there's still a ceiling. If you extrapolate this and build a scaling law, the ceiling is still 67%. So that's something that we didn't solve. We are just making the scaling law a little bit better, but not making it. We are still not able to make it tuneful forever to get 100%. So cool. I think I have 15 minutes. Any questions so far?
Sorry, this was with natural language, really?
Because in some sense, LLMs and humans are different, and we want to, offload some of the more tedious part of the work to the machine, and we hope that they have the expertise to do better than us. What is your intuition behind this, criteria that to want the theorem to be proven can be stated very concisely?
Sorry, so maybe, so how does this relate to elegancy? Because you feel like elegancy is not something huge.
No. I'm just thinking data is data, right? If you have a hard problem and the machine can train on, then it's being able to, prove these capabilities. So why is there even not?
Because, I'm not sure this is a good analogy, but like I think even in human world, right? Like there are areas where eventually all the statements are just messier. People are just dropping to a local minimum, and just you are not doing that interesting work. I think that's so basically we are just dealing with the failure mode that the large language model just start to work on the very messy stuff, which is not conceptually interesting.
I see. So you're thinking that that kind of more messy data kind of misaligned with what this model is trying to achieve is actually going to distract the model from getting to the right region with a
And you probably believe that fundamental elegant statements are more impactful for solving harder questions.
Of course.
It's more like a regular short description, thing. I think it's really a generalization essentially, right? Because in general, if you look around a problem, you would expect it to be elegant in the sense that you describe. But I think on harder problems, I think it's just hard to define what is them.
And another thing is that I think you made a comment that we are using AI to do all the tedious stuff, right? So, but I think for math, it's kind of like
the other way around.
Not the other way around. It's doing the tedious stuff as well, but but to go to AGI, it has to be better than humans. So it's not only about tedious stuff. Like the AI has to get intuition, get elegance, get all the conceptual stuff as well, which I don't know whether they have, but at least they seem to have some. Actually, when I talk to GPT 5.5, I feel like it understands elegancy to some degree.
So we'll recognize what's interesting.
Yeah, at least to some degree, right? Like it's not that bad. It's probably better than an undergrad for sure. Yeah.
Sorry, I have a question.
You get that dash fit. What model is it? How do you get the asymptote?
So this one is we fit a scaling law for this.
The dash line.
This one or this one?
Not the dotted line, the dash line. The one, the fit. It's fitting what?
Oh, so this one.
Yeah.
Oh, this is the performance. This is the you track how many statements you prove.
That's the color line. That's what the dash line do. Dash line is the kind of model that you fit to it.
So you mean this one or this?
Yeah, the legend you call it fit.
Oh, sorry. This fit means so. This means this. This legend is for this one. Maybe the legend is not great. Like this fit means this and this line. So, and does it make sense?
No, there's a dash line that goes through the data. So
This one, right?
Yes.
This is our algorithm. This corresponds to this legend. This is the algorithm that we design. The performance of the algorithm we design. So on the x-axis is the number of generations, number of conjecture and the proof generations.
One that is dash, one that is continuous.
The dash line is the fit curve, and the
fit in what?
Fit it to the data and
So okay, let's go through it because there's a pointer issue. Like I don't know which one you're talking about as a dash because there are so many dash lines. So this blue line is our method's performance, and that line is the ceiling for this performance. If you extrapolate to maybe
I get that.
Okay, yeah.
And in your performance, you have two lines. There's a wiggly line, which I presume that's the actual data. that your performance that you observe.
Yep.
And there's a line that goes through it that is in the legend, it's called fit. Like you fitted some kind of model to it.
So maybe ignore the legend. Are you talking about this one?
No, okay, never.
This one? This one?
Never mind.
Then this one?
Never
There's a
mind.
fitted curve.
The fitted curve.
How did you?
Oh, you mean the shade?
Yeah. No, the shade is a real thing.
Oh, you mean this? Oh, I see. I see.
Fitted one.
Oh, yeah. That's just you fit this logistic function in the log space, like a you build a scaling law for it. Yeah.
Oh, so it's a logistic model.
So you take the log of this, and then you fit a sigmoid.
And why such a good fit?
It's just because we don't know, like, that's the, I think some people here probably studied, like, I try to study a little bit, like the scaling law is is a mysterious thing, like, sometimes just some form just have very good fit. I think you can see from this paper, this meta paper, this is their fit. So this is the fit, and these are the real data, and somehow in log space, it's a reasonable fit. Yeah. And they fit many more curves like this, and they all seem to like this.
Okay, but you don't know exactly why.
We don't know. There are some theories.
It's a common one in computational dynamics that fit well, but it's not that.
No, nothing. It's just purely empirical. You try to find. Yeah. Yeah, and to be fair, actually, so this is a very subtle business because if you don't use this form that I described, you can use some other form which looks very similar, and so that the fit around here still looks, at least visually, sounds very similar, and then the number for the ceiling will be very different. So it's very sensitive to how you fit it. But I think here we're just trying to demonstrate that our ceiling is better than the other ceiling. We're in the same fitting schema. Again, this is not something you can trust 100%. Nothing you can trust 100%, because in the sense that if you change the data set, then maybe things are changing. So all of these are partial evidence for for the algorithms to work, but you cannot really prove it, right? Yeah. Okay, so I think I have like another 8 minutes. I have a few slides about some of the other works I have done in this space, just in case you are interested. So I'm gonna go through it very quickly. So one of them is that we are trying to reduce the latency of the prover by some divide and conquer. So so I guess you probably have used the ChatGPT Pro extended. I'm not sure I've done that. Like it takes like an hour to think about it. So we are thinking, okay, maybe you should parallelize it a little bit so that you can think first on hierarchically first think about some kind of like a general plan, and then you delegate each of the parts to some kind of like workers. So basically we design this, and nothing, the hard part is actually sometimes the implementation, but the high level idea is just that you design the model to do this. So you first generate some plan to decompose the problem, and then you delegate to each of these workers, and each of these workers is a separate thread in the GPU. They maintain a shared KB cache, and then some separate kind of other rollout. And you implement this, you train it in the same way as you test it, and you run some R algorithms, and you can see that the parallel length or the longest path length will become much shorter compared to no such training. And we did see that the decomposition of the statements are meaningful. We eyeball them. We use larger models to evaluate whether decomposition makes sense. So generally, the models becomes better at decomposing the statements into parallel parts. And wait, I think I have another work. Oh, I didn't have it. Another thing we are trying to do as well, if anybody is interested in offline, I can tell more. So is how to verify some of these statements. So like in natural language, so we have a verifier that can verify in natural language, not in Lean. And the kind of idea is also similar to this. You first decompose the problem into subparts, and then you verify each part. So basically, you first, in some sense, rewrite the proof into a more modularized situation, and then you verify each of the modules as opposed to verify the whole proof. And this also make it kind of like more accurate in verification. And I have a few slides about, some of the other works along this line. I guess hierarchical proof strategies is very popular. So there are a bunch of papers on how to decompose, so on and so forth. Some of them are just scaffolding. Some of them are involving training, like my paper. And there's a lot of like a kind of like in context learning, kind of like feedback loop, like alpha evolve, kind of like a kind of algorithms where you take the lean feedback and you give it back to the prover in context, and then you can generate better proofs in the next round. And Godel proof and seed proof are generally the best papers. The state of art kind of like models along this line of like using lean proofs and verification. So I think seed prover now can prove like 50% of the Putman bench questions. These are some citations. Okay, yeah. So I guess open questions. So I think most of the open questions are still open right now. So I guess developing a taste for elegancy, I think we try to do it, but I don't think what we are doing is the final right way. It's probably just a small step towards that. Avoid collapsing into one area of math. I think we still don't have a good idea for how to do this. It's not that easy to reproduce either. Like sometimes it just happens. So like it happens so at some random place, so that sometimes you fix you change your algorithm in other places, then your algorithm works better, and it doesn't happen until very late. So it's also a little hard to study it. And I think there's a general question about, this is probably more like an optimization question. How do you balance your effort on conjecture and proving, and how many steps you should do, on each of them, and some of this kind of like, how many rolls you do per statement for GRPO, for conjecturers and provers, because for both provers and conjecturers, you are using RL to train them, and their GRPO, SysPo, all of this kind of like optimization decisions. And generally, how to have a multi-agent system with more components, and you can give credits to each of the components. Do you define the roles of each component in what way? Are you just defining by prompting, or you define it by prompting the first time, and then you try to kind of distill the prompt into some kind of like, you try to have a reward for it, and then try to distill the prompt into the model ways. There are many different kind of ways to deal with it. It's a very complex system. And on a broader level, I think I think my agenda, as I try to argue for, is that whether we can have like other aspects of mathematicians' work that these algorithms are not capturing. For example, I think in mathematics, people do write a lot of survey papers and try to synthesize and try to simplify the proofs, make it more elegant, and find more abstract and clean proofs that are more broadly applicable. All of these are missing from this kind of algorithms, and certainly the algorithms don't set agenda or directions by themselves. They are given some kind of like statements and some kind of like rough idea on the target, but they are not. It's kind of like more there's no kind of like hierarchical kind of like agenda setting, right? It's more, everything is on the level of like a single statement proof. There's no like a program or something, right? Like in mathematics, I think I've seen people, design kind of a program and design a family of questions and some roadmap on how to solve them, which is not captured by any of this. Okay, that's everything I have. Thanks.